Ever tried running one of those massive, crazy graphic games on your phone? You know, the kind that makes you think your phone's about to blast off because it's working so hard.
Oh, yeah. I can practically see the heat warnings popping up on the screen.
Exactly. It's a struggle, isn't it? Turns out quantum computers kind of have the same problem. They rely on these things called qubits. It's like their processing power.
Right.
Now, qubits, they're super powerful, but they're also really sensitive and hard to come by.
It's like having a race car engine.
Yeah.
But you only have like a teaspoon of high-octane fuel.
Oh, we see what you're saying, you know?
There's so much potential for speed, but you're just limited by how much you can actually use.
And that is a perfect way to jump into today's deep dive. We're looking at a research paper with a really long title.
They always are.
I know, right? It's called Reducing Qubit Requirements for Quantum Simulations, using molecular point group symmetries.
Catchy.
I know, right? But it's all about finding these clever ways to do more with fewer qubits. Like, can we stretch that teaspoon of fuel further?
And what's really exciting is that this paper focuses on molecular simulations.
Which are essential for so many different fields.
Absolutely.
We could be talking about designing brand new materials, discovering life-saving drugs.
Oh, for sure. Or even like finally figuring out how photosynthesis works at a really basic level.
Exactly. And the key to all of that is understanding how molecules behave.
And that's where these quantum computers come into play. They have the potential to change everything about molecular simulations, but we're still stuck with that limited qubit issue.
Right, but that's where this paper comes in, right? It might have found the answer for us, and it's something we see every day. Symmetry.
It's hiding in plain sight.
Think about a snowflake. They have that beautiful six-fold symmetry.
And you know, molecules have symmetries too, just on a much smaller scale.
So what if we could use those symmetries, those patterns, to make our quantum simulations more efficient?
That's exactly what this research is all about.
It's figuring out how to explain those symmetries to quantum computers in a way they understand.
It's like giving them a set of shortcuts.
Like handing them a map with all the back roads highlighted so they don't get stuck in traffic.
Exactly. Instead of calculating every single tiny detail, they can just focus on the essential parts and get the same result.
Okay, I love that analogy, but let's get specific here. The researchers used the simplest molecule to prove this concept, H2. Just your everyday hydrogen gas with two hydrogen atoms.
And that's what makes it so good for explaining this. If you were to swap those two hydrogen atoms,
yeah,
the molecule would still look exactly the same.
Right, because they're both hydrogen atoms.
Exactly. And that's that nothing changes thing that tells us there's symmetry at play.
So instead of simulating both those hydrogen atoms separately, they realized they could just focus on one and basically cut the whole problem in half.
Working smarter, not harder.
Exactly. And by doing that, by using this symmetry that's already there, they were able to use half the number of qubits for the simulation.
That's huge, especially in the world of quantum computing where every little bit counts.
Now, I'm sure someone out there is thinking, well, that's fine for a simple molecule like H2, but most molecules are way more complicated than that.
You're not wrong, and that's where things get really interesting.
So we've got these simple symmetries figured out, but how do we apply that to bigger, more complicated molecules? It's not like we can just rearrange those atoms like a jigsaw puzzle.
You're right, you can't just do that. And as molecules get more complex, those symmetries, they get tougher to spot. But that's where this paper gets really cool. They've created this sort of universal translator for molecular symmetry.
A universal translator. Okay, now I'm really interested, but do we need to brush up on our quantum calculus to understand this translator?
No, not at all. The best part is you don't need to be a math whiz to get it. What they've done is they created this framework, like a set of tools, but mathematical ones, that can describe any kind of 3D symmetry a molecule might have.
So it doesn't matter how a molecule is flipped or turned, this framework can still find those hidden patterns.
Exactly. It's like having, imagine you have these special glasses that let you see the underlying symmetry no matter how complex the molecule looks.
I like that. Symmetry glasses.
Yeah.
So did they test this out? Did they use these symmetry glasses on a tougher molecule?
They did. They chose beryllium hydride. It's BH2 if you're looking for it on the periodic table.
Okay, and BH2, that's still a pretty small molecule, right?
Yeah, it is, but it has a more interesting symmetry than H2.
Gotcha. So I'm guessing this is where their framework really shows what it can do.
Definitely. See, other methods, even when they could find symmetries in BH2, the best they could do was reduce the qubit needs by 4.
Okay, so that's pretty good, right?
It's good, yeah. But this new method, it found a hidden symmetry that the other ones missed, completely missed it. And that meant they could use one fewer qubit in their simulation.
I know we keep saying every qubit is important,
Yeah.
but is one qubit really that big of a deal?
It's a huge deal. Think about it. Each qubit doubles what your computer can do. So dropping one is like taking an old, slow computer and turning it into something super fast.
Okay, so it lets us simulate more and faster.
Exactly. And we get those results much faster, too.
This is starting to feel like a win-win. We find these hidden symmetries, we save our precious qubits, and we get to run these simulations way faster. But something tells me it's not always this easy.
You're right to think that it's not always straightforward. You see, not all symmetries play nice with each other.
What do you mean?
Well, sometimes the symmetries within a molecule, they clash. It's hard to use all of them at the same time.
So it's like trying to fit different shaped blocks into a box. Some of them just won't fit no matter how hard you try.
Perfect analogy. The researchers found that with some types of symmetries, you have to choose which ones you're going to use to get the best simulation. You can't use them all.
So we're not just looking for symmetries, we're trying to figure out which ones work best together.
Exactly. More complex molecules, yeah, they might have more symmetries, but it's not about using all of them, it's about choosing the right ones.
Okay, so it's a balancing act.
It is, and to show this, the researchers looked at the ammonia molecule, NH3.
NH3, that's another step up in complexity, right?
It is, and that means even more symmetries to work with.
So more options, fewer qubits needed. It's got to be good news.
It should be, but remember what we were saying. The more complex the molecule, the harder it is to pick that perfect combo of symmetries.
Right. It's like having a toolbox with every tool you could imagine. Knowing which ones to actually use, that's the tricky part.
That's a great way to put it. So we're not just hunting for symmetries, we have to be smart about using them.
Okay, this is starting to feel less like chemistry and more like some kind of high-stakes quantum chess game.
That's an interesting way to think about it, but you're right. What's really interesting about this research is that it's not just about finding symmetries, it's knowing how to use them.
I love all of this, but let's bring it back down to earth for a second. What does all of this symmetry stuff actually mean for us in the real world? Why should we care about saving a few qubits here and there?
That's the million-dollar question, and that's why I'm so excited about this research, because it's not just about making computers faster. This stuff has the potential to really change the world.
So we've gone from not having enough qubits to playing quantum chess with these molecules.
Mm-hmm.
It's clear this is way bigger than just making simulations a bit faster. This feels like the start of something huge.
I'd say so. This is about getting those quantum computers to really flex their muscles and tackle the big problems. You know, like those life-saving drugs and incredible new materials we were talking about. This gets us closer to making those a reality.
So what does that future look like? What changes when we can run these super complex calculations faster and better?
Imagine a world where we can create personalized medicine perfectly tailored to your genes. We could discover drugs so much faster and make treatments way more effective.
Okay, that's huge. What else?
And picture engineers making materials that are stronger and lighter than anything we've ever seen. We could revolutionize everything from airplanes to buildings.
It sounds like we're talking about changing the world here. And this research, with its focus on symmetry, this is a big part of making that happen.
Exactly. We're setting the stage for a future where we can simulate even more complicated systems, things like climate change. If we can accurately model how those greenhouse gases mess with our atmosphere, we can come up with better ways to fight back.
So it's not just about how fast these simulations are. It's about tackling those big, complex problems that affect everyone. It's going from tiny molecules to the whole planet. It's kind of mind-blowing.
And what gets me really excited is that we're just getting started. This research changes how we approach quantum simulations. We've got this amazing new set of tools to find and use symmetry, but there's still so much more we can do with it.
It's like we found a treasure chest, but we've only opened the first few compartments. What's next? Where do we go from here?
Well, one really exciting path is to build even smarter algorithms, ones specifically designed to use these symmetries we're finding. Imagine if an algorithm could just look at a molecule and automatically know the most efficient way to run the simulation. It would pick the best set of symmetries every time.
So taking that quantum chess game to a whole new level, the computer becomes the grandmaster.
Exactly. And beyond just finding them, what if we could design algorithms that change those symmetries on the fly during the simulation? Always optimizing for efficiency. Talk about a game changer.
This feels like a call to action for all the brilliant minds out there. It's like firing the starting pistol in a race to see who can unlock the true power of these symmetries.
I love that analogy. And it's a race I'm definitely watching. This paper has blown the door wide open, and I have no doubt that researchers are going to find even more amazing ways to use the power of symmetry in their quantum simulations.
Well, there you have it. We've journeys from the limits of qubits to the elegant world of molecular symmetry, and I have to say, the future of quantum computing has never looked brighter. It's a future full of incredible discoveries just waiting to be made, and it's all thanks to the power of patterns and a little bit of quantum ingenuity.
Who knows, maybe the next big breakthrough in medicine, materials, or even our understanding of the universe is going to come from a cleverly placed symmetry in a quantum simulation.
Until next time, keep those brains buzzing, and remember, sometimes the most elegant solutions are the ones hiding in plain sight, just waiting for us to unlock their secrets.